Oh, wait, you're listening?
Okay.
All right.
Okay.
All right.
You're
Listening
to Radiolab.
Radiolab.
From
WNYC.
C
Yep.
and NPR.
Kristen Shaw is a whore. Kristen Shaw is a whore. Look at her dance. Look at her go. Look at her dance like a whore. Kristen Shaw is a whore.
Hey, I'm Jad and Robert.
Kristen Shaw is a whore.
I'm Robert Krulwich.
Look at her dance. Look at her
This is Radiolab, and today,
Today it's all about
loops.
things that happen over
And over.
and over
And over.
and over
And over.
and over.
And over. Coming up, loops that hurt you.
Strange,
Loops that heal you.
dangerous things.
Loops that scare you.
Loops.
And loops that eat you.
And loops that incomplete you.
A what?
Shh.
Kristen Shaw.
Hey, I'm Jad Abumrad.
And I'm Robert Krulwich.
This is Radiolab, and this hour we're talking about
Loops.
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 Okay. Loops.
Something and nothing, nothing and something, something and nothing, nothing and something.
Here's one for you.
I mean, zero is the obvious loop, and its loop shape is part of why zero is zero.
Who's this?
This is Alex Bellos.
And I'm the author of Here's Looking at Euclid.
Nothing and something.
When I was a kid, I used to think, oh, zero, it's just like the hole with nothing in it. But actually, zero was chosen by the Indians as kind of reflecting like the eternal cycles of the faces of heaven.
Something and nothing, 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 nothing.
The Romans and the Greeks and the Jews, we didn't have a zero. We just had, everything started at one. And one reason why we didn't is that we were kind of afraid of the void.
Afraid of the void. What? Like
Well, I mean, how would you describe something
Something,
that isn't there?
nothing.
There's nothing to say.
Is that scary somehow?
Yeah, it's an emptiness and a nothingness, and it means you're so alone you don't even know where you are.
And so this sort of was a psychological barrier to us grasping this zero. But in India, everything and nothing was the same thing. They had this very sort of fluidity, and they grasped this idea that nothingness was something.
And oddly enough, the way they decided to represent the nothing was they took a little piece of nothing and they drew a circle around it, which turns the nothing into a something.
And it's a loop.
And it's a loop.
Something and nothing, nothing and something, something and nothing.
So this idea of eternity and continuity and infinity is actually contained with our numeral for zero. I mean, I kind of love the idea that actually he is kind of the most mystical, kind of magical, spiritual digit of them all, and we use it every day.
Okay, ready?
Okay.
This is Radiolab.
Oh, okay.
Yeah, you start. Yeah.
Okay. This is Radiolab.
Today we're talking about loops.
I'm Robert Krulwich.
I'm Jad Abumrad. This is Radiolab.
It's all about loops.
Yep, I'm Jad.
And I'm Robert. You're listening to Radiolab.
Today we're talking about loops.
I'm Robert.
I'm Jad.
And it's all about loops.
Yep, I'm Jad.
I'm Robert.
We're talking about loops.
And speaking of things that happen over and over and over again on this show here,
Hello.
here he is again,
Hi, Jad.
Hey, Steve.
Stephen Strogas,
How are you? Mathematician.
Cornell University.
How's it going?
I'm good.
And Steve told us a story about a mathematical loop
That threw mathematicians all over the world.
for a loop. Story starts way back with a guy named...
Gottlob Frege.
Gottlob Frege? How do you spell
Yeah,
Gottlob?
it's not Gottlieb. It seems to be L-O-B at the end, unless it's a typo in every book I've ever seen.
Now, to set this up very quickly, Gottlob Frege was a mathematician back in the 1870s and 80s, and he had a dream that mathematics could unlock the secrets of the universe. That you could maybe even build a machine, feed it some basic mathematical rules, and it would just start churning out discoveries.
Wouldn't even need a human being.
That's how powerful he thought math could be.
But that led him to a question. If math is the most fundamental thing in the universe, what is the most fundamental part?
Of math.
What's at the foundation? Is it numbers? Is it, 1, 2, 3?
Well, that's what you would think.
But Gottlob,
He said, no, there's a deeper thing than numbers. The deepest thing of all is what today we call sets, the set of things,
Set.
Yeah, so like what's a set? You could...
Steve explained it to us using, of all things, Sesame Street.
Really old episode.
As far as just to set it up here, it's two people working at the Furry Arms Hotel. There's Humphrey.
All right, Ingrid,
who's got a green nose and a pink face, and his girlfriend, I don't actually know what she is. She might be his wife, Ingrid. And so they're hotel keepers, and Ernie is in the background.
Hold on.
And so Ingrid and Humphrey are taking an order,
Hello, how may I help you?
room service order from a room full of penguins.
We're hungry.
You know, Humphrey says, "I'll take your order, Mr. Penguin, sir."
What would you like? A fish. Fish. A fish. 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 Fish.
Then Humphrey says, "Let me check if I got that right."
Fish. 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 You got it.
And then he calls over to Ingrid, who's going to call it into the kitchen. So he tells Ingrid,
Fish. 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 Fish.
and Ingrid says, "Fish, fish, 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 fish."
No.
And Humphrey says, "No, that's not right."
Fish. Fish.
Because she only says it 5 times. But then Ernie explains,
Excuse me, Ingrid and Humphrey, I have a better way for you to do this.
A better way.
Count the fish.
Fish.
1,
Fish.
2,
Fish.
3,
And-
4, 5, 6 fish.
Holy mackerel!
they both realize, Ingrid and Humphrey, how powerful this is. And they say, "Does it work
on
for
other stuff? Say cinnamon rolls?
Yep.
spark plugs?"
Absolutely.
Wow.
That's the point, that what cinnamon buns and spark plugs and fish, the sets, have in common is that there are 6 in each. Right? I mean, if you try to say, what does 6 really mean? It's the thing that those sets have in common.
According to Steve, it's not so much the number 6 that's important here.
Yeah, that's just a label for this characteristic that all these piles seem to share.
It's the pile itself, the set.
That is the most basic thing.
So Frege said,
Holy mackerel!
well, this is it. Sets are
The bedrock.
that I've been looking for.
Yeah, we can build the rest of math on top of it.
Yeah, and then I can make my math machine that'll solve the universe.
And I think he published a book sort of showing how this might work, except that Russell
Bertrand Russell, the mathematician.
then found a devastating paradox that ended up, well, annihilating what Frege had tried to do.
Russell's paradox has now become known as
The Barber paradox.
It's a little thought experiment. So in this case, the set is a town.
Yep.
A town with people,
Yep.
one barber.
with the following rules.
In this town, the barber shaves everyone who doesn't shave himself.
The barber
Sounds reasonable,
shaves
right?
everyone who doesn't shave himself.
So some people shave themselves, some people go to the barber.
That's the universe. We're in a town where everyone who doesn't shave himself is shaven by this barber. And now the question is, who shaves the barber?
Who shaves?
Remember, the barber has the property that he shaves everyone who doesn't shave himself, so he can't shave himself. But on the other hand,
Couldn't he?
if he doesn't shave himself, then he's one of those people who doesn't shave himself and is therefore shaven by the barber.
Well, maybe the barber. Here's 2 solutions for you guys. The barber could not shave. Couldn't he just not shave? Maybe.
No.
Or maybe
everybody
he
in
could-
town shaves.
Maybe he could set up some sort of mechanical device that's sort of like one of those Rube
No,
Goldberg
you
things.
can't do that. You can't
Yeah,
change
you can't
the
answer
rule.
sensibly what happens to the barber.
And no one has.
There's nothing to say. He either does or doesn't shave himself by ordinary Aristotelian logic, because the barber can't shave himself and he can't not shave himself. So there's
And
something.
that's what ruined the machine that would solve the universe?
Wait, this
I
seems...
think it could ruin an afternoon, or maybe you have to wait for a couple hours, like after lunch, before you go swimming. But I can't see that like overthrowing all life's work.
It does. It does. It turns out to be very, very problematic for the foundations of math.
Because what this barber paradox, the reason it was so annoying to mathematicians was that math is supposed to be this logical thing, right? Logic is the lifeblood of math. And yet here, you had this little bit of math that was illogical, a self-contradicting set.
But Bertrand Russell, the guy who came up with all this, he didn't lose faith. He thought, well, this is just a problem with set theory.
So then he spent a long time trying to make a theory. I think he called it a theory of types instead of sets. And he had certain admission rules that he thought would prevent paradoxes from happening.
And for a while, it was looking pretty good. Under Bertrand Russell's system,
There was no logical problems, no paradoxes, until
this scrawny little German guy comes along. And you say his name Gödel?
I hear it often pronounced, well, I don't speak German, but mathematicians often say it like the woman's piece of clothing, from the old days. It's something like Gödel.
Good.
So there's a kind of sound in the middle.
Umlaut.
This is Jana.
Jana Levin.
She has written a book about Gödel.
And I'm a professor of physics and astronomy at Barnard College.
And she says the point at which Gödel enters our story, it's 1930s, Vienna, Austria.
He had just recently finished his, what would be equivalent to like a doctoral degree, a PhD.
Smart dude.
Kind of a rising star. It was no question that people around him understood that.
But he was also maybe a little bit off.
He had real breaks with, reality. He was, in the biographies, they'd call him a paranoid schizophrenic, but he seemed more a kind of obsessive depressive. I don't know if my armchair psychology terms are accurate, but he was in and out of sanatoria, and he had real difficulties being sure what was real.
The only reality he really trusted was math.
Circles,
shapes,
prime numbers,
formulas, axioms.
Right.
And at a certain point, he got into paradoxes. Perhaps it was the Barber paradox that lured him in, we don't know. But he began to think about and actually experiment with some of these paradoxical loops.
So he took something like the paradox of the liar. The paradox of the liar says, this statement is a lie.
This statement is a lie.
Right. If it's true, then it's false. And if it's false, then it's true.
This statement is a lie. If you think about that too much, you might explode.
Right.
So Gödel was interested in that phrase, and for various reasons, he took it, tweaked it a little bit to come up with
the following statement. This statement is unprovable.
This statement is unprovable.
Which is very important to notice. If it's provable, then it's unprovable.
Obviously a little bit of a word game, but Gödel thought, forget words. What would happen if I converted this statement into math? Because in math, things are either provable or unprovable. They cannot be both at the same time. It's either true or false. And if it's true, well then damn it,
you should be able to prove it.
Yeah.
So he said, I'm going to assign a special number, a unique number, to make that a purely mathematical statement by coding it in a very clever way into arithmetic.
To be honest, we don't completely get this part.
It's very, very clever.
But once he did his mathy stuff, he had a rigorous mathematical statement right there on the page. He looked at it and he realized that what he just said in math
is that the following statement.
This statement is unprovable.
Is?
It's true because it's actually unprovable.
Meaning, in math, this statement actually is unprovable. Because it is true, the logic of math will not let you prove that it is true. So it might be true. We'll just never know.
Nothing like that is supposed to happen in math. Things are supposed to be true or not true.
And you're supposed to be able to prove every true thing, says Steve. So if there's something true that you can't prove, that means that the math is strangely, woefully incomplete.
It's always called his incompleteness theorem. That's the phrase. The Gödel incompleteness theorem is that if you have a system of axioms that are consistent, meaning they don't contradict themselves, they're necessarily incomplete. That is, there are certain statements you can make within that system that you can't prove or disprove. And all of math has this character. This is the big shock, that this is not just about word games, about logic puzzles with barbers. This is as devastating for even just counting, for 1, 2, 3, 4. In other words, math is shot through and through with these kind of statements that you can't either prove or disprove. Seriously, the deep thinkers at the time were amazed at this. It was recognized as one of the great ideas of the 20th century, for sure, maybe of all time. I mean, maybe I should make it more concrete. There's a question that, as far as I know, is still not solved.
Steve gave us this example of a problem.
Something called Goldbach's conjecture.
That kind of gives you a sense of what incompleteness feels like.
So Goldbach's conjecture says that you can always write any even number as a sum of two prime numbers. So let me give you some examples of that. Like, say, 12.
Yeah.
Remember, first of all, prime number means you can divide it by 1 and by itself, like 7 is a prime number. You could divide by 1 and 7, but nothing else.
Okay.
All right, so 12, which is an even number, is 7 plus 5.
Those are
both
primes,
prime numbers.
Yeah. Mm-hmm.
All right, let's try another one. How about 24? That's 11 plus 13.
Right.
Okay. Or 36, 19 plus 17. Any even number. Now, this has been checked out to, I don't know what, billions, trillions, maybe hundreds of trillions. So no one has ever found a counterexample to Goldbach's conjecture. And here's the thing. You might think that either it's true or it's false. It might be that this statement, every even number is the sum of two primes, it might be neither true nor false. but what we today call undecidable. Undecidable is a term that comes from Gödel.
Undecidable.
Yeah. I mean, suppose in some ethereal or transcendental sense, like that is, suppose that there's God, and God knows that this is true. Then, what about us here among the world of human beings? All we can do is check each even number, and every time we check it's true. That would never constitute a proof, because we'd never run out of numbers.
If you then say that to understand everything, you either have to defer to God, who does understand everything if you believe in God, but if you don't believe in God, you then have to live with mystery and not knowing.
Mm-hmm. Yes.
That's all you can say? Mm-hmm.
I'm going to say yes. I'm going to say well, I think you've encapsulated it perfectly, and I think that Gödel himself was, I think, a believer in all kinds of mystical things. Like, for him, this was very freeing and liberating because it meant that we couldn't be mechanized. There was profound mystery forever.
Hold on. I'm on your team here, but let me just point out something. Gödel, when he died, he was not exactly liberated.
Yeah.
He was a paranoid. Like, he thought people were trying to poison him. He starved himself to death. He wasn't exactly liberated.
Well,
in the end.
but I choose to believe that somewhere in his tortured mind, and I guess his mind was pretty tortured, there was a little fellow humming a song of liberation.
This problem's unsolvable. 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 This problem's.
Thanks to Steve Strogatz, he's currently working on a new book which he calls The Joy of X. Not sex, just X. We don't even know what he's experiencing the joy of.
And Jen 11, her book about Gödel is called A Madman Dreams of Turing Machines.
This problem's unsolvable. This problem's
And let's begin.
Message 3.
This is Sean Mackey at Stanford University. So, looks like the credits.
This is Jana.
This is Steve Strogatz.
Radiolab is produced by Jad.
I call him Dad, and Kristen calls him Chad, but his real name is Jad Abelrad.
Our staff includes
Alan Horn.
Alan Horn.
Soren Wheeler.
Soren Wheeler.
Sean Cole.
Sean Cole.
Pat Walters.
Pat Walters.
Tim Howard.
Tim Howard.
Brenna Farrell.
Brenna Farrell.
And Lynn Levy.
And Lynn Levy.
With help from Jonathan Mitchell.
Douglas Q. Smith. Kristen Clark.
Rose Eveleth. Rachel James.
And Matt Keatley. Kilty.
Special thanks to Joe Fragola
and Dr. Elliot Crane.
Bye, guys. I'm calling from jury duty.
End of mailbox.